My name is Lin Ye, and I'm a PhD student in Indian University in the supervision of biomechanics. Okay, so nowadays people use finite element methods to understand the process and principle of the application, and the parameters in the model will significantly affect the application, simulation results. So we consider two important factors. One is the thickness of the capsule, and the other is the material property of the lens. So our model profiles were derived from the refractive index contour of the human eye lens. So we used the spline curve to fit the refractive index profiles in the SolidWorks and build a quarter model of each lens. The cortex of the lens was divided into many layers, and each layer was assigned different material properties. So, to study the effect of the material property of the lens on simulation results, we selected two different lens material properties. So the difference between the two material properties reflect in the old lenses. In the data of Fisher, you can see the nuclear modulus is much smaller than the cortical modulus. But in the data of Waddell, when it goes to the 40-year-olds, the nuclear modulus is about half of the cortical modulus, and after 40 years old, the nuclear modulus gradually exceeds the cortical modulus, and when it goes to the 48 years old, it's about twice the cortex. These are the specific material values used for each layer of the model. The Young's modulus varies uniformly between layers, and the average value of the modulus of the cortex is consistent with the value in the literature. So here, this is the data from the Waddell used in the model. So you can see that the modulus in the 48-year-old model gradually decreased from the nucleus to the surface. This is the sagittal view of the model. In our models, there are three groups of suspensory ligaments. Each group contains 17 zonules, which will be shown later. The insertion position of the anterior and posterior zonule is 1 millimeter to the equator, and the anterior and posterior zonule are tilted 15 degrees. So we want to see if the uniformity of the capsule had an effect, and also if the thickness of the capsule had an effect. So in our model, the capsule was constructed as either variable thickness, thin constant thickness, and thick constant thickness. For the variable thickness, we use the data from the barricade. So the capsule of the capsule from the anterior pole to the equator and the posterior pole to the equator were divided into 100 equal parts, and these six locations from the anterior pole to the posterior pole were given a specific capsule thickness as listed in the table. That's a slide. Okay, and the capsule thickness between each pair of the location varied evenly. The constant thickness was determined by averaging the value of the variable thickness and taking values at 1 micron either side of the average. So this figure shows the 4 models with mesh. From these figures, you can clearly see there are 17 donors in each group here, and they are evenly distributed on the lens surface. So this is the bone methylene stress result for all the lens models with different capsule thickness using features data. Okay. So red color in the figure represents the maximum stress, and the blue color represents the minimum stress. And the second column of the figure is the lens with thin constant thickness capsule, and the third column represents the models with thick constant thickness capsule. So for the 16-year-old lens, the variable thickness capsule model has higher stress in the cortical region than the constant thickness capsule. You can see, especially you can see it here. It's bigger in the variable thickness capsule, and the 48-year-old lens shows a similar trend. For the 35-year-old lens, the stress and the stress distribution are very similar in all 3 models. And in the 40-year-old lens, the cortex towards the equator has this bigger stress in the variable thickness capsule. So this is the result using the data from the Wiley law. In the 16th and the 48-year-old model, the stress in the variable thickness capsule is higher than the uniform thickness capsule, but the difference is not significant. In the 35 years and the 40 years old, the variable thickness capsule has a lower stress, and it's more obvious in the 40-year-old lens. So maybe you have noticed that the stress distribution in these models are very different from the previous models. So let me put them together. For the 16-year-old and 35-year-old models, the use of the different lens materials lead to different stresses. But the trend of the stress distribution is consistent. That is, the stress gradually increases from the nucleus to the surface. Okay. For the 40-year-old model, when using the data of Wiley law, the stress in the anterior cortical region is bigger, and the stress in the posterior cortical region is smaller. The small stress also occurs in the peripheral region here in the posterior cortex. For the 48-year-old model, the maximum stress occurred near the equator in the cortex, and the stress in the anterior nucleus is relatively large compared to their modulus. Compared to the other models. In contrast, the stress on the cortical surface is the smallest. This huge difference is due to the difference in the numerical properties. So here we also consider the radius of curvature and the COP variation of all the lenses under different capsule thickness. And this is the result based on the data of Wiley law. So you can see that the capsular thickness has a significant effect on the 16-year-old lens. You can see from 2.97 to 2.1, and 2.14 to 1.15. Okay, and it has little effect on the 48-year lens. So for the variable thickness, yes, the variable thickness, the effect of the variable thickness depends on the age. In the 16-year-old lens, the variable thickness has the same effect of the thick constant thickness capsule. In the 35-year-old lens, it depends on the material used, and in the 40-year-old lens, it produces more COP change and uniform thickness capsule, and in the 48-year-old lens, they are very similar. So, in conclusion, the capsular thickness as well as the choice of the material properties influence the results of the modeling and the simulation of lens shape change. These factors need to be taken into account when using modeling to investigate condition, explosive with age, and for optical design of novel implant lenses with accommodative capacity. Thank you for your attention.
Any questions? I'm excited to be here today to share our research on age-related changes in cortical and nuclear stiffness that contribute to accommodative loss. And this work was carried out under the guidance of my supervisor, Professor Wang and Professor Personic. Okay. As we get older, many of us find it is more difficult to focus on near objects. This condition is known as presbyopia, which typically begins in the 5th decade of our life. And many studies have reported that the lens becomes stiffer with age, and its size and shape also change over age, both of which are key factors in accommodative decline. And our study aims to investigate how these changes in lens material properties and geometry contribute to the loss of accommodation. Additionally, we examine the differences in zonia function between the different age groups. And we hope this study can help us get a deeper understanding of how these factors affect the lens ability to focus. To investigate those age-related changes, we developed a series of finite element models that simulate lens behavior during accommodation. And we divided our models into 3 groups based on age. The first group consists of lens samples from individuals in their 4th decade of life with material and geometric parameters that reflect this age. And the 6th group includes lens samples from individuals in their 6th decade with corresponding parameters. And in the mixed group, we combined the parameters from both 4th and 6th decades to allow for comparative analysis. We analyzed the contributions of lens geometry by comparing the 4th and mixed groups and assessed the impact of material changes by comparing the 6th and mixed groups. We obtained the lens geometry from biomechanical measurements taken from lenses in a tension-free state using a central radiation facility. However, we know that because the shape of the isolated lens differs from that in a fully accommodated state. So we used a pre-stress approach to account for this difference, and this method was developed in our previous research, and my supervisor has explained it in detail. So we first simulated the lens, the transition of the lens from the isolated state to the unaccommodated state, which allow us to acquire the lens shape and initial stresses needed for the formal simulation from unaccommodated to accommodated state. And the synchrotron-based measurements provided us with crucial data on lens geometry and refractive index distribution, as we can see in this figure. We extracted the refractive index along this line, and its profile shows that a relatively flat center and a steeper gradient surrounding regions. And we calculated the first order derivative of this curve. And based on the positions of the two turning points, S1 and S2, we can identify the points N1 and N2 in this profile. And used the average refractive index of these 2 points. We can use it as a threshold to distinguish between the nuclear and cortex, and we can get this figure. The innermost circle is the nuclear boundary, and the outermost circle is the lens shape. And our model also accounted for the relationship between anterior zonia shapes, age, and lens equatorial regions. And all parts of our lens models were consumed to be linear, elastic, and homogeneous. And the elastic properties were from the spin measurements by Weld. And we assembled this pre-stressed lens model to an eyeball model to get a complete model, and then we performed a formal simulation that activates based on the initial stresses. Okay, that's our result. Our result shows that the differences in the posterior radian of curvature of lens surface and nuclear surface, as well as the thickness, were more pronounced between the mixed and 6 growths than between the mixed and both growths. And then we developed the optical lens model in the Zmax based on these geometric parameters, and calculating the effective focal length and its reciprocal of this focal length gives us the central optical power, COP. And the differences in the lens deformation and the COP changes between the mixed and 6-decade growth were greater than those observed between the mixed and 6 growth. This suggests that the lens material properties play a more significant role in influencing lens deformation and COP changes. And the change in COP was not statistically between the groups with similar material properties but different lens shapes. the COP change in the force groups was about 1.4 times greater than the mixed group. So it can, this indicates that the length geometry also involved in the accommodative decline. So we further explore the analyze the trends and slopes of the length geometric parameters during accommodation. As change in COP increases, the length surfaces become more curved, and the thickness increases and the cortical diameter decreases. We observed the consistent trends across both groups, but varying slopes. Notably, the mixed groups exhibited steeper slopes than the force group, suggesting that lengths with older geometry require more deformation to achieve similar changes in COP compared to the younger lengths. And next, we examined the zonier forces and found that the magnitudes of zonier tension were similar among all groups, and with consistent distribution patterns. The anterior and equatorial zones carried out the majority of tensions. And when we investigated the zonier angles, we discovered that the force group had the lowest anterior and equatorial zonier angles and the greatest angular change. And the other two groups with similar length geometry, this group and this, they exhibited similar angles and angular changes. This finding stressed that the length shape affect length zonier angles, and the maximum tensions and angular changes in the anterior and equatorial zones highlight their crucial role in accommodation. Lastly, we explored the effect of the nuclear to cortical stiffness ratio on accommodation. We found that the model with a higher ratio exhibited lower change in COP. However, models with the same ratios but different average stiffness values exhibited similar change in COP. This indicating that the stiffness ratio is more crucial than the general stiffness values. And in conclusion, our study shows that the most significant contribution to age-related change in the length comes from its material properties, which have a greater impact on length deformation and the COP alteration than shape and size. The increase in the nuclear to cortical stiffness ratio appears to be the main pathway through which change in length material properties lead to accommodative laws. Additionally, while age-related change in the length do not affect the distribution of zonier tension, they do influence zonier angles, and the anterior and equatorial zones appear to be the major involved components in the accommodative process. And these are some biomechanics related works, and that's all. Thank you for your attention.
Thank you for a nice talk. I'm not in the field, so I'm going to ask a bit naive question. But as far as I understand it, it was very interesting to hear that you said the change in stiffness between the cortex and the nucleus might be one of the key factors. Can that stiffness be accessed somehow in a real lens, in a crystalline lens? Can it be related to protein concentration or something?
You mean the stiffness ratio affect the real lens?
Yes.
Okay. We can say in this figure. A little. Yeah. In this figure, the cortical nucleus to the cortical to nuclear ratios in the real lens is more increased than with an age. That's actually a situation. So we use this situation into our models settings. So we get the result as shown.
You hear me now? Yeah. So you asked about protein concentration. The protein concentration doesn't change, but the protein state does. So the proteins, as they change with age, their relationship with water changes. There's more free water, and that's probably what's having something to do with it. But I say probably it's something we're still looking at. But it's really an excellent question, and that's exactly what was said. You know, the link as well between mechanics and proteins. That's something we need to work on.
So, to restore accommodation to the presbyopic eye.
Is it more important to restore elasticity to the nucleus or to the cortex?
That's a really good question, actually. With younger lenses, it's been found that the nucleus is the bit that stretches. But I think it very much depends on how the lens has aged. And what we have found, Yutian showed about lenses in the 4th and 6th decade, but even within that decade, there's a huge amount of individual variations. And I think it very much depends on the protein changes. It depends a lot on the state of health. I mean, protein changes are much more complicated. And that's the crystalline proteins. We're not talking about the water channel proteins, the aquaporin proteins, and that's the water transport ones. So the question is really, which ones are you looking at to change the flexibility? There are a couple of hypotheses. One is the crystalline proteins get more aggregated and they get stiffer and so on and so on. It's a really simplistic model. The other one is that perhaps the water channels proteins are changing and they're not distributing the nutrients in the water to the proteins. And it's something that there's a whole bunch of work that Keha and I are doing on mutations in this area, so it's a kind of watch this space thing, but we don't really know. We are talking about, there's a lot of these compounds now that people are advocating for softening the lens. We're not entirely sure, but we've got some results from spring this year actually, but it's something we're working on. But it is very pioneering stuff. Yeah. Thanks. Sorry, I shouldn't be answering questions. I'm the moderator. Anybody else?
Maybe I missed this information from also from other talks. Are there any methods to visualize the stiffness or to map the stiffness somehow in the to see these differences? Are there any experimental methods to map those the differences in stiffness between nucleus and cortex in vivo? Apart from radar and scattering, I don't know.
Not of which we're aware, not in vivo.
Not indeed.
OCTL star.
But does it map that?
But it has. I'm not really sure if you can see this from OCT, but.
What would be developed? Anybody else?
Thank you. A few years back, there was a trend to improve elasticity of the crystalline lens by making incisions with a femtosecond laser in vivo. And there was one trend to do radial incisions, and another one to separate the cortex from the nucleus. And there were some early results comparing the two methods. I don't remember which exact application, but I remember seeing those papers 10 years back. Maybe this is something interesting to look at the surgical literature of the time.
Based on Shaka, as we know, as we both know one way or another. That was based on one's theory, and yes, there were some changes. How long lasting they were, I don't know, I haven't really followed it. Perhaps the next VPO, they might go on doing the talk. So I don't know. And so I'd like to thank everybody for this session.